NENOMATICA, where mathematics meets YouTube excellence. In this short lesson, we will prove a clean symmetric identity built from the roots of a quadratic. Our goal is to show that the square root of x1 over the square root of x2 plus the square root of x2 over the square root of x1 equals south over the square root of p. Let x1 and x2 be the two roots. We use the classic symmetric notation, s equals x1 plus x2, and p equals x1 times x2. Step 1. Combine the two fractions using a common denominator. The common denominator is the product of the two square roots, namely square root of x1 times square root of x2. Step 2. Simplify each product of identical square roots. Square root of x1 times itself is x1, and similarly for x2. Step 3. Use the symmetric definitions. Replace x1 plus x2 with s, and replace x1 times x2 with p. Quick recap. Start with the original expression, combine over a common denominator, simplify the radicals, and then substitute the sum and product s and p. In this short lesson, we will prove a classic symmetric identity for the roots of a quadratic. Our goal is to show that the absolute value of x1 minus x2 equals the square root of s squared minus 4p. Assume x1 and x2 are real roots of some quadratic. Let capital S be their sum and capital P be their product. So s equals x1 plus x2, and p equals x1 times x2. To build intuition, look at a number line. The distance between the two roots is the absolute difference, the length between x1 and x2. We now carry out the algebraic proof step by step. Step 1. Define capital A to be the distance, that is the absolute value of x1 minus x2. Step 2. Square both sides to remove the absolute value. Step 3. Expand the square. Step 4. Rewrite x1 squared plus x2 squared using the square of a sum. Step 5. Substitute s for the sum and p for the product, and simplify. Finally, since a is non-negative, take the positive square root. Recalling that a was defined as the absolute value of x1 minus x2, we conclude the desired identity. This formula depends only on the symmetric data s and p. It does not change if x1 and x2 swap, which matches the idea that a distance ignores order. Proof complete. In problems, you can compute s and p directly from the quadratic coefficients using Vieta relations, and then use this identity to get the distance between the roots instantly. In this lesson, we will solve a problem using symmetric expressions in the roots of a quadratic. Here is our system. We are given x1 squared plus x2 squared minus x1 x2 equals 7, and the quantity x1 plus 2 times x2 plus 2 equals 20. We want the quadratic with these roots and the roots themselves. Step 1. Expand the product in the second equation. We use distributive property to get 4 plus 2 times the sum of the roots plus the product equals 20. Step 2. Introduce symmetric sums and products. Let s equal x1 plus x2, and p equal x1 times x2. Also recall that x1 squared plus x2 squared equals s squared minus 2p. Step 3. Substitute these into our system. The first line becomes s squared minus 2p minus p equals 7. The second line becomes 4 plus 2s plus p equals 20. Step 4. Solve the linear equation for p and substitute. From the second line, p equals 16 minus 2s. Substitute into the first line to get s squared minus 3 times the quantity 16 minus 2s equals 7. Step 5. Simplify and factor. Expanding gives s squared plus 6s minus 55 equals 0. This factors as s minus 5 times s plus 11 equals 0. So s can be 5 or negative 11. Step 6. The quadratic with roots x1 and x2 is t squared minus st plus p equals 0. Because p equals 16 minus 2s. For s equals 5, we get p equals 6, and the quadratic t squared minus 5t plus 6 equals 0. For s equals negative 11, we get p equals 38. The discriminant is s squared minus 4p equals 121 minus 152, which is negative 31. So no real roots. Step 7. Solve the accepted quadratic and check. Factoring t squared minus 5t plus 6 gives t minus 2 times t minus 3 equals 0. So the roots are 2 and 3. Check in the original conditions. 2 squared plus 3 squared minus 2 times 3 equals 7, and 4 times 5 equals 20. Both hold. Therefore, the quadratic with real roots satisfying the conditions is x squared minus 5x plus 6 equals 0, and the roots are 2 and 3. In this video, we will evaluate a symmetric expression built from the roots of a quadratic. We will mirror the textbook step order exactly, and explain each move visually. The quadratic is x squared plus 5x minus 1 equals 0. Let its roots be x1 and x2. We must compute capital B equal to the fraction with numerator x1 cubed times x2 plus x1 times x2 cubed, and denominator the product of two terms x1 squared plus 6x1 plus 3, and x2 squared plus 6x2 plus 3. Because x1 and x2 are roots, they each satisfy the quadratic equation. We will rewrite the two denominator factors using that fact. First, for x1, x1 squared plus 5x1 minus 1 equals 0. Therefore, x1 squared plus 5x1 equals 1. Add x1 plus 3 to both sides. The left becomes x1 squared plus 6x1 plus 3. The right becomes x1 plus 4. We repeat the same steps for x2. Now substitute these two equalities into capital B. Each denominator factor simplifies to x1 plus 4 and x2 plus 4. In the numerator, factor x1, x2. Expand the denominator product to prepare for symmetric sums. Let S be the sum x1 plus x2, and P be the product x1, x2. For ax squared plus bx plus c equals 0. The relations are S equals negative b over a, and P equals c over a. Here a equals 1, b equals 5, c equals negative 1. Thus S equals negative 5, and P equals negative 1. Also, x1 squared plus x2 squared equals s squared minus 2p. Substitute these into b. Plug in s equals negative 5 and p equals negative 1. Work the arithmetic carefully. Therefore, the exact value of capital B is 27 over 5. In this example, we will evaluate a symmetric expression in the roots of a quadratic. We are given the quadratic x squared minus 5x minus 1 equals 0. Its roots are a and b. We must compute capital A equals a squared over b plus 1 plus b squared over a plus 1. We'll proceed step by step, turning everything into sums and products of the roots. Step 1. Put the two fractions over a common denominator. Multiply a squared by a plus 1, and b squared by b plus 1 over the product a plus 1 times b plus 1. Step 2. Expand the numerator and the denominator. In the numerator, we get a cubed plus a squared plus b cubed plus b squared. In the denominator, a plus 1 times b plus 1 equals 1 plus a plus b plus ab. Step 3. Group the numerator into power sums. That is, a cubed plus b cubed plus a squared plus b squared, all over 1 plus a plus b plus ab. Step 4. Introduce symmetric sums. Let s equal a plus b and p equal ab. We will rewrite the numerator and denominator using s and p. Step 5. Use power sum identities. A cubed plus b cubed equals s cubed minus 3ps. A squared plus b squared equals s squared minus 2p. Substitute these into the expression for capital A. Step 6. Combine like terms in the numerator. We obtain s cubed plus s squared minus 3ps minus 2p, all divided by s plus p plus 1. Step 7. Use Vieta's formulas from the quadratic x squared minus 5x minus 1 equals 0. 4x squared plus bx plus c equals 0. The sum of the roots is negative b, and the product is c. Here s equals 5, and p equals negative 1. Step 8. Substitute s equals 5, and p equals negative 1 into the simplified expression. Compute the numerator and denominator to get the exact value. Recap. We combined the fractions, grouped as power sums, rewrote everything with s equals a plus b, and p equals ab, used the identities for a cubed plus b cubed and a squared plus b squared, applied Vieta's formulas s equals 5 and p equals negative 1, and obtained a equals 167 over 5. In this example, we will evaluate a symmetric expression in the roots of a quadratic. We will follow the exact sequence of steps shown on screen. Given the quadratic x squared minus 8x plus 1 equals 0, let alpha and beta be its roots. We are asked to compute capital A equal to the fourth root of alpha to the beta over beta to the alpha plus the fourth root of beta to the alpha over alpha to the beta. First, use the sum and product of roots formulas. The sum alpha plus beta equals negative b over, which is 8. The product alpha beta equals c over, which is 1. Therefore, alpha equals 1 over beta, and beta equals 1 over alpha. Now, we rewrite the expression for capital A once more before substitution. Substitute beta equals 1 over alpha, and alpha equals 1 over beta into A. Because 1 over alpha to the alpha equals alpha to the negative alpha, each denominator moves to the numerator. So we get alpha to the beta times alpha to the alpha inside the first fourth root, and similarly for the second term. Combine exponents with the same base. Add the exponents. Using alpha plus beta equals 8. Each fourth root becomes the fourth root of the eighth power. The fourth root of alpha to the eighth is alpha squared, and similarly for beta. Now use the identity alpha squared plus beta squared equals the square of the sum minus 2 times the product. Substitute the sum equals 8, and the product equals 1. Compute the final value. 64 minus 2 equals 62. In this lesson, we will solve a problem about symmetric expressions in the roots of a quadratic. The strategy is to rewrite the given expression in terms of the sum and product of the roots, then solve step by step, and finally compute the difference between the roots. We are told that alpha and beta are the distinct roots of the quadratic ax squared minus ax minus b equals 0. We are also given the numeric relation 40 beta squared plus 20 alpha squared minus 20 beta equals 17. Our task is to find the difference of the roots, the absolute value of alpha minus beta. Step 1. We rewrite the left-hand side so that alpha squared plus beta squared and beta squared minus beta naturally appear. Watch the grouping. Step 2. We normalize the quadratic by dividing both sides by a, which is not 0. That gives x squared minus x minus b over equals 0. Therefore, the sum of the roots s equals 1, and the product p equals negative b over a. Also, because any root satisfies the equation, for beta, we have beta squared minus beta equals b over a. Step 3. Replace alpha squared plus beta squared by s squared minus 2p, and replace beta squared minus beta by b over a. With s equals 1 and p equals negative b over a, we obtain one clean equation in b over a. Step 4. The difference of the roots equals the square root of the discriminant divided by the absolute value of the leading coefficient. Here the leading coefficient is 1, so it is just the square root of the discriminant. The discriminant of x squared minus x minus b over equals 0 is 1 squared minus 4 times 1 times negative b over, which is 1 plus 4b over a. Substitute b over equals negative 1 over 20 and simplify. In this example, we will use symmetric expressions in the roots of a quadratic. Example: the quadratic is x squared minus 4x plus 1 equals 0. Without solving the equation, we want the values of capital A and capital B, where a equals x1 squared minus x2 squared, and b equals 1 over x1 cubed plus 1 over x2 cubed. First, recall Vieta's relations for ax squared plus bx plus c equals 0. The sum of roots, s, equals negative b over a. The product of roots, p, equals c over a. For our equation, a equals 1, b equals negative 4, and c equals 1. So s equals 4, and p equals 1. We also need the discriminant delta, which is b squared minus 4ac. That equals 16 minus 4, which is 12. Now, we compute capital A. Use the difference of squares x1 squared minus x2 squared equals left parenthesis x1 minus x2 right parenthesis times left parenthesis x1 plus x2 right parenthesis. The second factor is the sum of roots, which is 4. For the first factor, we use that the absolute value of x1 minus x2 equals square root of delta over a. Therefore, a equals 4 times the square root of 12, which simplifies to 8 square root 3. Next, we compute capital B. Rewrite B as x1 to the third plus x2 to the third, divided by left parenthesis x1 x2 right parenthesis cubed. Use the sum of cubes identity x1 cubed plus x2 cubed equals s cubed minus 3ps. Substituting s equals 4 and p equals 1 gives b equals 64 minus 12 over 1, which is 52. Example, we will use symmetric expressions in the roots of a quadratic. Given the quadratic x squared minus 4x plus 1 equals 0, without solving for the individual roots, compute capital C equals x sub 1 to the fourth plus x sub 2 to the fourth, and capital D equals square root of x sub 1 plus square root of x sub 2. First idea, Vieta's formulas. For a general quadratic, ax squared plus bx plus c equals 0, the sum of the roots s equals negative b over a, and the product p equals c over a. In our case, it equals 1, b equals negative 4, and c equals 1. So s equals 4, p equals 1. Now compute capital C. Start by rewriting x1 to the fourth plus x2 to the fourth as the square of x1 squared plus x2 squared minus 2 times x1 squared x2 squared. But x1 squared plus x2 squared equals s squared minus 2p. And x1 squared x2 squared equals p squared. Substituting s equals 4 and p equals 1 gives c equals 16 minus 2, all squared, minus 2 times 1, which simplifies to 194. Next, compute capital D equals square root of x1 plus square root of x2. Square both sides to get d squared equals x1 plus x2 plus 2 times square root of x1 x2, which is south plus 2 times square root of p. With s equals 4 and p equals 1, d squared equals 6. Both roots of the quadratic are positive, so d is positive. Therefore, d equals square root of 6. Final results. Capital C equals 194 and capital D equals square root of 6. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.